Hello friends, this is View to X-ray Co Kiran. Today I thought of making a very short video on transmission lines. With me there are four types of transmission lines. A couple of them are commonly used, you might have seen, and a couple of them are not commonly used, but I just wanted to share because I use them for a couple of my applications in amateur radio. This is LMR 240 equivalent from India. It has got better characteristics than RG58. It is lightweight and it has got higher losses than RG213, but better than RG58. So I use it for 40 meters and 80 meter field applications. It is even lossy even for 25 meters length of cable for higher bands like 20 meter and above. This is the second type of cable which was very popular in the earlier TV days. It is called ribbon cable or flat cable. It is typically made up of two conductors held in parallel with the PVC, and typically it has got 300 ohms of characteristic impedance. In coaxial cables, most of the coaxial cables are 50 ohms, and there are a good amount of cables with 75 ohms used in CATV, cable TV applications and satellite applications as well. But traditionally hams have been using 50 ohms cable, and 300 ohms cable used in folded dipole applications in television reception. Nowadays cables are a little bit rare to get in the market as well. I got this from my old stock of cables I had. This type of a flat cables have got other applications as well. They come in various sizes. This is 300 ohms. There is 450 ohm ladder line as well, which looks very similar, but it has got windows inside. It's also called window line, I think. And then there is a ladder line which is a 600 ohms cable. Third one, which probably most of you are familiar with if you are using a hexbeam type of antenna, is this rigid coaxial conductor transmission line, which has got a square tube or a cylindrical tube with inside there is another coaxial conductor. In this case it is a copper conductor. This very specific application for VHF antennas stacking, kind of a quarter wave splitter. You feed from this point, take divided equal amount of power from these two places. So it is also called as a 3 dB splitter in some cases because it divides the power into two. It is useful for stacking antennas and combiner as well. This is the second feeder or transmission line, and the third one which I have, and I had designed it 10 years back, similar one for hexbeam antenna only. This is also called a parallel strip conductor or rigid line strip conductor. In this case there are two L angle aluminum with the center foam insulator out here. So basically the distance between these two conductors and the width of the L angle matters a lot. So it is fed from the top using any transmission line, and since the distance is maintained appropriately with the insulator in between, the 50 ohms characteristic impedance is maintained. This same principle of power splitting and other transmission line properties also can be uniformly maintained with this. This is slightly simpler to build than the coaxial line as per me, but only problem with this is the weatherproofing. If water seeps into these areas, the characteristic impedance changes. Same thing happens with any other parallel line conductors. So the medium in between plays a lot of role. Just to show, this is my hub made up of old backlight plate and some PVC pipes in this line. with the wing nuts connecting. I made it for 3 bands as a feeder, 20, 15 and 20, 15 and 10. Rest of the lines I don't need it during the contest. I plan to utilize this in the contest only. So this is all made up of hot water pipe. So that's it about this. I will quickly go to the computer and show the app CAD model for couple of these elements, how actually we can design it. AppCAD is available from this site hp.woodshot.com. This is a free software used for designing microwave and RF circuits, simple to utilize. So you go here and download using this link here. Once it is downloaded and installed, you open up this AppCAD. AppCAD has got multiple menus on the left side here. You can see that it has got circuit designs, it has got active circuits, various other things including the transmission lines, which is of topic today. I will talk about two things which I have used. So first thing which I will show is the microstrip, which is the design which I had for the L angle aluminiums which were joined together to form a strip line in the center there. Okay, so what I did was I came to this microstrip designer. There are few things which you will have to be concerned about. In certain cases, this diameter or the width of these strips, here it is considered as a ground plane or yellow line, lower yellow line. There is a dielectric separation. Dielectric is a material in between these two strips. Length units are here specified. I will consider them as mm, and I will consider around 21 megahertz as frequency. And right now it is a free space. I will keep everything else as default. Okay, and then we will calculate Z0, which is a characteristic impedance of this line. If we separate two conductors with this dielectric, what is the characteristic impedance? So now we can see that if it in the free space, it is 80 ohms. So the more the distance you go between the two lines, the more the characteristic impedance will be. At the same time, the dielectric constant also matters. Here it simplifies very much. So we can see that there are a lot of things listed out here. Earlier in 2012, I had designed one feeder using PTFE, that is Teflon, available in local market. Aim is to get as close to 50 ohms as possible for this frequency range, and ensure that we have practical aspect of this also cleared. So we cannot have a very broad flat metal pieces in our transmission lines because of the practical reasons. It may be wobbling, maintaining the gap is difficult. So we will make it optimal for our use. In this recent trial, which I used rubber silicon. Here also the moment I use rubber silicon, dielectric has increased to 3 from 2.1 of PTFE. But normally it is a slightly approximation for us because we don't know actual composition of material we use. I used single-sided foam tape and to cut to 3/4 of width and applied across this particular plane between the two conductors. So these were actually L angles to facilitate my other connectors from the sides to the elements. It is not just a simple plane of flat one side strip. It was like having wings on the other sides as well for the practical reasons. So when I make this type of arrangement, it drops to 40.51. So if I increase I think the distance, so I had to play with increasing the distance by including silicon in between. The silicon sealant used generally we get for fixing the glass mirrors and all that in Indian market. I also used nylon nuts and bolts to connect these two pieces together and tighten it and loosen it up to get as close to 50 ohms so that I can measure. I connected my VNA and terminating the other side with 50 ohms load, and so I had to play with the distance as well as the materials which I have. So material I don't have much control, because once it is selected as a foam tape, I had to just place that, and only way I could get it through is by the distance. In this case I used a 7 to 8 mm distance as per this, but in reality it was around 5 to 6 mm. Once you know how to measure the impedance of this line, it is easy. So similarly I used other line for my VHF splitter. I used this coaxial calculator. In this, I think it was 1 inch by 1 inch surrounding. So let us say this is 1 inch is in mm, it is 25. Half-inch copper tube, which was around 12.5 mm. This was around 25 mm. So it comes to be approximately 48.5 mm. So once we align a square tube and round tube within, and use some rubber bushing between in intermediate spaces, I used, I think, for half a meter line, which is near to the quarter wave line out here. So this particular area, if you see, this gives electrical length of this. Here 1 meter for 145 megahertz means 0.484 lambda. So you can actually see this varying by varying the distance also, like the length of the line also, 1050 mm. So I can approximately come to length required for that transmission line to be quarter wavelength. In my case it was a quarter wavelength, so it was around 500 mm, that is half a meter. It was around this 520. Let us make it as a 520. It comes to be around 2.25, which is very close to quarter wave line. So I used these copper lines, and I drilled holes from the top sections to connect to the lower conductor. This would be the ground plane, and this is the inner core. So you actually have to isolate these two areas with simple round rubber bushes in 3 or 4 places in between, so that distance is maintained and this line is as straight as possible. You have to weatherproof this particular area, because water seeping in will vary this dielectric and then vary the overall characteristics of the line. So hope this helps. This was a very quick introduction on how I designed my transmission lines required for a very specific application. Single port antenna analyzer would be sufficient for this testing of these transmission lines. Thank you very much for watching.